our next goal here is to motivate our stopping criteria for while loops. Okay, and so we still don't really know what a while loop is, but it's going to be a lot like a for loop, but it's going to run until it hits some desired um, threshold. Okay, and but to motivate that is what I want us to do is to actually vectorize our code here that we used yesterday when we were trying to approximate e to the x. Okay, and actually yesterday I think we were doing just e to the 1 there, but if you tested it out for different values of x, you would have noticed that our code did a good job of approximating e to any power. Okay, and to vectorize this, all I really mean is that we're going to collect all of our approximations and put them into a single vector. Okay, and so one thing for those of you who have had some coding experience is you might be used to indexing things, or having them start with an index of 0, but we're actually, in MATLAB, we start with 1, and this is because we're usually talking about matrices and vectors whose first entry we typically in mathematics would call, the first entry, not the 0th entry. Okay. So here I'm just saying that our first entry in the vector and maybe I should even specify up here what this actually I think it's pretty clear. Our x equals 1 is associated with this formula up here, but then next down here we want to also try to vectorize our for loop. Okay, so we want then the next spot in our vector to contain the next approximation. And so we can do that just simply by saying that we want the I plus 1th approximation to be equal to the ith approximation plus x to the I over I factorial. And so this will get the job done here. I'm going to run the code so you can see it, and you can see that our output here in the end should be this vector that contains all of our approximations of e. Okay. All right, and let me move this. You can see that this doesn't really look like a vector here, right? I mean, it says columns 1 through 11. Okay, and these are all our approximations, but if you come over here, it'll look a little bit more like a vector if I actually click this. Okay. All right, and so you can see all that. But for what I want to do here, it might actually be more helpful if this was a column vector rather than a row vector. And there's an easy way to do that in MATLAB. Okay. There's actually several easy ways to do this, but I'm going to click out of here. Okay. So the easy way to switch this is you can just put a little apostrophe here. Okay, and so what the apostrophe does is it gives you the transpose of the vector or matrix that you're working with. Okay, so that'll fix that problem. And then another thing is I'd like to see a few more decimal places. So I'm going to switch this to format long. There we go. And you can actually see, I don't even need to go over here and click this one now. You can see that these are stacked nicely here. Okay. And what I want you to notice is that the further we go down this list, the further out our accuracy goes. Okay, right? You can see that there's not much of a difference between these approximations the further down the list we go. Okay, and I think again yesterday we kind of noted that our approximation was accurate up to about 7 decimal places to begin with, but we're not always going to know what the exact value of something is. And so the best way to tell whether we're actually converging on something or not is just by taking the difference of our consecutive approximations. And so as that difference gets smaller, we know that we're getting closer and closer to, you know, what that series is converging to. Okay. And so another thing we could do is we could add in here, I'm going to write it as EA because that's what our textbook does. But we could look at, for one, I'm going to actually change this a little bit, but we could just look at the difference between each consecutive, let me write it in here. Yeah, there we go. Yeah, we could look at the difference between each consecutive approximation, and hopefully that difference is getting smaller. We are technically going to look at the percent error here, but I just want to start off with this just so you can see that these differences are getting, you know, smaller and smaller and smaller. Okay, and you know, perhaps we want to vectorize this as well. How about we do this? There we go. Done. Okay. So the first entry in here will just be the difference between, you know, our second and first approximation. The second entry will be the difference between the third and the second, and so on. Okay. I am going to suppress the intermediate calculations. But in the end here, I would like to see this vector. Okay. All right. And again, you can see that these differences are getting smaller and smaller and smaller. And this is the key, again, to noting that we are converging. Okay. And so it would actually be sufficient for most things we do to think about this as our stopping criteria. When we hit a difference that is small enough to satisfy our needs, we can stop. Okay. But you will notice that it's pretty common to actually think about the error in terms of percent error. So as what we would do is we would take the absolute value of these two, and we would divide it by the current approximation. Maybe I could throw in a little something here. Okay, so absolute relative error, and again, we'll be thinking actually of it as a percentage. So in the end here, I'll multiply it by 100. But I want to write out what this actually is. This would be our new approximation minus our old approximation, and then divided by our new approximation. Okay. So looking at this relative error, again, gives us an idea on whether we're converging or not. And the only, again, difference here that I'm going to add is we're going to be thinking about this in terms of percent. Okay. But let's go ahead and look at this percent absolute relative error. I know it's a lot of words there. Okay. And I'm going to tack on that times 100 there as well. Okay. And so you may notice something actually kind of odd here. You might see this 1.0 e plus 0.2 times all this stuff here. So all that really means is this is just scientific notation. This is really just saying 100 times all these values. Okay, and so this is a common thing for MATLAB to do here. But again, you can see that these percentages here are getting also smaller and smaller and smaller. So you might be wondering why we're looking at relative error opposed to just the difference between our consecutive approximations. Okay. And the idea is that this is going to better apply to different problems. Okay, and here's what I mean. when we think about just finding the difference between consecutive terms, it honestly means something very different when we're talking about extremely large numbers and extremely small numbers, right? A difference of, 0.0001 when we're talking about large numbers, um, that's a very small change. But when we start thinking about the small numbers, 0.001 might be actually a very large difference. Okay, and so to kind of account for the fact that we're thinking about numbers of varying magnitudes, we're going to choose to look at relative error instead. Yeah. Now that we can see why we might want to use relative error here, rather than just, again, the difference between two consecutive terms, we're going to jump into looking at a while loop to solve this problem, and then we will turn it into a function.